Okay, guys, let's get a little bit more real world as well. Let's have a look at a design for a rectangular table placemat. Have a look at this example. A new design for a rectangular table placemat. A placemat, by the way, is like a little plastic rectangular object that you put on the table when you could put your food on that as well. Okay, so it's like a placemat. They call it, it's like a little plastic mat. And it's been implemented by a company manufacturing or making dining room items. That's for the where you eat. On the two width sides, that's the little width sides of the rectangular placemat, two white semicircles are pasted as shown in the diagram. The remaining area has been shaded with a multicolored pattern. So have a look here. So here's your little mat. We're going to call that width X, and notice they pasted on here two little semicircles. They're equal in size, and it's pasted over here, and then we painted that. So you've got a nice little design for a little rectangular table mat that you're going to sell. And what you do is you put your plates of food onto this mat so you don't damage the table. Now let's see. Now what's the first question is, says show that the shaded area, that's the thing painted, the multicolored area, is given by this, and determine the maximum shaded area possible. Okay, now let's see how we're going to approach this. Very simple. Okay, you know that this is X, that is the width. Okay, now the other thing that's important here, if we go back and look, which they didn't say, and I think they didn't mention this, but I'm going to add it in anyway, which is important, is that what we've got here, and this is some information that was left out, they probably would have had a little errata sheet, and they said that that's 100 centimeters there. Okay. All right. All right, so once we've got that, we can, this nice little placemat for the table, and we've got that 100, and that's X. Now what you know as well is that if you think about this, that's X. So this is the radius, which is a half of X. And that's a half of X there. Okay, now remember this also works on the other side. This will be a half of X and a half of X, that piece there, the radius of the little semicircle. Okay, now what we've got, if you've got two semicircles, we can put them together and have a full circle. And by the way, what is the length, or how would we get the area of the shaded bits? Well, if we think about it, the shaded area is going to be this little shaded area here, would be really the area of the rectangle, of that rectangle there, this full guy, subtract the area of really a full circle. If you think about it, you've got, if you put these, if you combine these two things, you're going to have a full circle. Okay, what do you do here now? What is the area of a rectangle? Length times breadth. So if you take this length, so the area of this is going to be length times the breadth, 100x. Okay, now the area of the circle, or which is made up of the two semicircles, what's the area formula? Look at this. Pi r squared is the area of a full circle. What's the area of a semicircle? Pi r squared divided by 2. But because we've got two equal half circles, we put them together and we've got a full circle. So we're going to say the full rectangle here, subtract pi r squared, which is pi. The radius is x over 2, and we square. Okay, so that's an important principle that we need there. Now let's see if this is of any use to what we want. Okay, let's just go back. Okay, 100x minus pi over 4x squared. Let's see if we can do something here. Okay. All right, so we've worked that out. Now I'm going to go and see, okay, let's see what we can do. We've got the area, the shaded area being 100x minus pi r squared. Now let's see if we can work it into the form that they want. Okay, that's 100x minus pi times x squared over 4. And guess what? That's the area in terms of x is 100x minus pi over 4x squared. What a pleasure. Okay, now the question in B says we want to maximize this area. How do we do that? Very simply put, how do we go? Have a look at this. We can say the derivative is what? Now careful, is 100 for that. Now careful with this. minus pi over 4 multiplied by, bring down the 2 and subtract 1. So your grade or the derivative here is 100 minus pi over 2x. 2 goes into 4 twice. Okay, and what do we know? What happens for a maximum or minimum? We are going to put the derivative equal to 0. So we plonk it equal to 0 there, and it's 100 minus pi over 2x. Okay, and if we go back and look at what the question said, it said determine the maximum shaded area possible. Okay, and firstly, of course, we're going to need the value of x to be able to do that. Okay, so let's just go through this again. We said the shaded area is the rectangle minus the 2 semicircles. Okay, we went through the process of differentiating, and then we've got this. So what if we have a look at that? Now all we can do is, I think I'm going to bring that pi over 2x to the other side. So I'm going to go pi over 2x is equal to 100. Okay, and multiply both sides by 2, giving me 200, and you divide by pi. Now once you've got that, all you do is you go and substitute that back into there, and you can then get the value of the maximum area of this thing. Okay, stay with us. We're going to pursue another problem, but this time in 3 dimensions. Don't go away.